Archiving started.
Yes.
Actually, okay. Hi.
Good.
Good.
Hi, my name's Stephan Fitzpatrick, and in this version, the other version I made, I have my name and the GPC logo on it. Let me just let you know that. This one is blank, by Anon. Anyway, I'm talking about something I investigated when I was doing geology school, called Europa, investigating the possibility of subsurface ocean. I'm going to be approaching this, I'm going to be tackling this mostly from a geological standpoint. So we're doing something called planetary geology, but it's all tied together. The boundaries start crossing over. Let's turn. Okay, Europa is the second Jovian satellite. They're also called the Galilean moons, after Galileo Galilei. He discovered them. And there's a couple of pictures of Europa. Those are kind of famous pictures. They're false colored. It's almost colorless, actually. And the four largest Jovian satellites are called Galilean moons because he discovered them in 1610. And there they are, the four Galilean moons, in order outwards. I believe it's Io, Europa, Ganymede, and Callisto. Io is extremely hot, the most volcanic body in our solar system. They're all named after women that the god Zeus was with. Jupiter, Zeus, king of the gods.
One of them is not a woman.
Yeah, and
Yeah. Europa, he came to Europa as a bull. You can use your imagination there. We're going to stop there. This was ancient Greece, different culture. Okay? Let's move to the next slide. Oh yeah, there's some facts on Europa. Semi-major axis, longest of the overweight ellipse is 671,100 kilometers. Mean radius, it's not too huge. Surface area, surface gravity, escape velocity. It's pretty moon-like. It has oxygen on its surface. To me, that's very interesting. That's an interesting little blip right there. There is oxygen on its surface. It's not because gravitationally it's holding oxygen to its surface. It's because oxygen is escaping from somewhere inside Europa, in the cracks in Europa. Some process is allowing oxygen to escape. Okay, the photographic indication is that there's dramatic variation to Europa's terrain. I mean, look at all this stuff. It just looks like nothing but a bunch of faults and fractures. Actuality, the vertical features are real slight. Once you get on the surface, apparently, there's very little variation. You're mostly going to see a flat, cold, icy surface. It's ice. It's nothing but water ice surrounding Europa. That's closer to the actual appearance of Europa. Pretty colorless. Okay, that's the composite map that they made of Europa. That's a full surface map. That's the entire surface of Europa. You see a lot of interesting things going on here. You see what they call chaotic terrain. You see lineaments that crisscross the globe that look like giant arcuate fractures or faults. Faults might actually be closer to what they are. The terrain on Europa resembles Arctic ice flows. They've got names for several different kinds for the terrain that they have on Europa. You have cycloidal ridges, these ridges that are circular shaped. You have domes, slightly raised features, lineaments, which crisscross the entire globe. Something called chaos, which is chaotic terrain. It's just a jumble. You see a lot of it in the Arctic. You see photographs taken from a plane of the Arctic and the Arctic sea ice. You see a lot of, especially in summer, you see a lot of this cracking occurring because there are a lot of forces at play in the ice. It's sinking, it's kind of bobbing up and down. You've got differential melting. That's probably what's happening here. Many of these images appear to be refreezing patterns of ice. They're all over the place. Something's got to be going on to create these patterns. And we've got to always remember that the surface is nothing but ice. Okay, another picture. Lineaments crisscross the globe. And these lineaments can form ridges. Okay, and they've done this. We've gotten our information from Galileo, the Galileo flyby, and also Voyager, more from Galileo. And from all the analysis, even the tallest structure is only about 100 meters. And these are those ridges formed by the lineaments. Those lineaments are the largest geological structures on Europa. And we think of it geologically too, because ice is a mineral. In fact, ice is often a metamorphic mineral. It has the same structure, so you've got to think of ice as a mineral. Okay. You got the names of some of those. You see all these names, okay, you've got Europa, so Europe, all of the names tend to be Celtic deities or Celtic mythology. That's a good explanation of the whole thing. It's kind of neat. Chaos terrain. Okay, you bunch of ridges and fractures, they're enmeshed, there's no obvious rhyme or reason. They call it chaotic terrain. And chaotic terrain happens on other bodies other than Europa. I mean, we get chaotic terrain here on Earth, like I was talking about in the Arctic. You've got ice rafting. This happens in the Arctic. So you've got a lot of similarities here. Something is happening to make this stuff crack, and it's moving it around in some fashion. Okay? All right, this is Quill Crater, I think it's a Welsh name, a Welsh term. It's one of Europa's youngest geological features. It's an impact crater. It's an impact crater that doesn't have the same features that other impact craters have. When you put an impact crater down on maybe a mass of granitic rock, you end up with something that's very pronounced. This isn't that pronounced. It's not very high, it's not very low. It's disappearing. And it's been disappearing very quickly, geologically, for quite some time. So we're thinking, what got thrown up, what occurred, and where did the impactor go? Oh, it's 26 kilometers in diameter. It's not very big either. Okay, well, when you're dealing with this kind of ice, you're dealing with conditions that are very different from Earth ice. For the ice that we think of in the Antarctic or the Arctic, or even the ice we see in winter. It's about 15 different types of ice. They're all structurally different. Now, this ice forms at extremely low pressures, extremely low temperatures, and there's some researchers who've looked into this, and they've hypothesized that the ice on Europa is a super fast cooled type of ice that mimics structurally a type of a type of rhyolite. It's got plagioclase in it, called perlite. It's microcrystalline in structure. See the next slide, please.
Can I ask something about that?
Yeah.
That dashed line there, is
Yeah.
that the conditions as you go down into Europa?
That's the hypothesized. That's the hypothesized line for conditions on and in Europa.
As you go down.
Yeah. They're thinking, this is your zone of conditions right here. Yeah.
And you're probably going to get to this, but I'm just curious about the fractures and all that. I mean, what variation is there in the pressure and or the temperature on the surface? I mean,
Very little on the surface. So you're thinking there's very little on the surface. What's happening? There's got to be pressure. There's got to be some form of pressure or kinetic energy from somewhere. It's not on the surface. It's cold and dead. There's hardly anything. There's a slight wind that comes off of Europa due to the stuff coming off of Jupiter. It sends out a wind from Europa. stuff that surrounds Europa, but other than that, there's nothing going on. It's got to be something going on underneath. That's part of the reason.
Is the entire surface of the moon exposed at some time to both the planet and the sun?
That's a good question. Europa is tidally locked. It's in synchronous orbit, meaning one side of Europa is always facing Jupiter, much like our moon. Here's some of the ideas about perlite. Okay, they think that it's glass ice, and that makes sense because you get glass, like if you get a lava that erupts on off of Kilauea, it turns into obsidian glass because it's quenched, especially if it hits water, it quenches quickly, and the crystals aren't allowed to grow. You get something called a cryptocrystalline ice. Well, they think that the ice on Europa, at least the surface, is very similar to that. It behaves, they've done tests, there's a couple of guys that wrote an article in Geology magazine, we'll see that in the citations, but they think that it mimics a rhyolite glass called perlite. And they tested it, cracked similar to the ice on Europa. Just a group of people out of a pretty large group of people in general who are investigating this planet kind of on their own. We'll look into that later.
Can I ask a stupid astronomer question?
No.
Perlite, I know that I go to Home Depot and buy perlite and I mix it in with my soil.
It is. That's what it is.
Okay.
Yeah. It's used as a sort of a boost for your soil, for your potted plants. That's
Okay.
exactly what it is. Volcanic glass. Volcanic materials tend to be high in nutrients. That's why you got a volcanic area, you can grow a lot of vegetables. There's a lot of nutrients in volcanic soil. Yeah. Very valid question. Okay, these are ice flows on Earth. Yeah, kind of similar. There is, we took these using satellite-based remote sensing instruments for comparison. The ice on Europa is thought to be briny, a lot like Earth's ocean. You see some of those false-colored images. They're adding false color to areas that they've detected using remote sensing instruments on Galileo as having a different chemical composition. And using these spectroscopic analysis, determines that there's a lot of brine coming up from somewhere onto the surface of Europa. Not just halite, which is NaCl, but a lot of sulfides. So you basically have your chlorides and your sulfides. You have those two, and there's a lot of sulfur coming up onto the surface of Europa, which I find a little odd. Okay, chlorides and sulfates. I'm sorry. Next slide. Okay, there's a comparison. Kind of similar, but not too similar. But you got to think. This is a smaller square area. This is tighter than that. That's probably measured in kilometers. That's probably measured in meters. So it might not be fair to compare them too closely. But we're just illustrating that we need further evidence. It really looks like there's liquid water down there. It really looks like there's a decoupled outer surface, decoupled from the rocky interior, but we don't have very much, we can't have any ground truth until, we do more.
But haven't some of our studies of the magnetic fields and the induced magnetic fields from Jupiter shown that there is definitely conducting fluid material?
Yeah. A lot of it has to do with the gravitational pull of Jupiter, as well as the orbital resonance from the other two inner Galilean moons, especially Io. It all starts at Io. It'd be cool to go to Io, but I wouldn't survive the trip. Okay, there's the two models NASA came up with a while back, actually. There's one is the convecting ice model. This is for the skeptics. It's slush. It convects because it's a mineral, just like our mantle. Our mantle convects. These are the bottom two are the ones I like. That we have either thick ice or thin ice, and there's a liquid ocean. The outer crust is decoupled from the inner rocky, probably silicate, or definitely silicate interior. Those are the two models. Most people like those two models because it'd be cool to have an ocean down there. Okay, which one is it, thick or thin? That's what's on the table right now. That's what people like Richard Greenberg are trying to determine. Okay, there's a artist conception. It looks like a thick ice model. And you see, you got the ocean and you got the slush. You have diapirs, you have warm ice, you have cold ice. So that's convective flow. That's a lot like our mantle. Okay. Okay, since the ice on Europa is thick and cold, how could ice possibly, and thick being relative, even the thin ice crust would be about 1 kilometer thick. Well, it's tidal forces from Jupiter and the other moons that act to flex the interior of Europa. Now, Jupiter and Europa are tidally locked, which means there's one face of Europa that's always facing Jupiter, okay? So you actually, even though Jupiter has an enormous amount of gravity that affects Europa, it's locked to where that might not produce a whole bunch of heat. Also, Europa's in orbital resonance with the other moons, with the other Galilean moons, actually. And there's a regularity and a periodicity to their orbits, and it's explained by something called the Laplace resonance. That's the formula for it right there. You ultimately end up with 180 degrees. Nice wave. And it results in a stable system. Okay, even though there's a little bit of give, it's basically a stable system. Not all orbital resonance systems are stable. This one actually happens to be stable. Oops. Okay, that's okay. Due to a slight lag produced in the motion of its orbit with Jupiter, it's not in perfect orbit. There is a slight lag. So something's giving, something's pulling at it. And once again, Jupiter has enormous gravitational attraction to all of its moons. Okay? There's a slight give, and it's exacerbated by the resonance between Europa, Io, and Ganymede. So there's a slight flex that occurs inside of the silica, whatever silica crust, mantle, whatever's way down there, flexes a little bit. And that flex causes friction. That friction causes heating. And this, kind of aside, this fracturing allows salt water to erupt on the surface, indicates some kind of motion or heat within Europa. But again, there's really nothing going on outside. It's hardly anything. So something's going on inside to make these fractures. These are globe-spanning lineaments. Yeah?
You said there was, how do you have warm ice?
Warmer than normal ice. Like ice that's close to freezing and it's kind of slushy, kind of like that stuff that gets on the road, you know, where it's still there. It's warm enough to get slushy, but it's not cold enough to refreeze it. Yes, you have different regimes of ice. I'm sure somebody, probably Richard Greenberg's, mapped it, you know, or come up with models. Because right now all we can do is come up with models, basically. We have information, but to actually, you know, go, okay, I'm going to make a cross-section of Europa that's got the thick ice with the slush, with the water, and then, you know, the crust and the mantle and all that. We have to use models to do that.
So the freezing is done, all the conditions are the same there, what you hear?
Yeah, pretty much, except I mean, you're dealing with a different battery of, you know, chemicals, and you've got, of course, that enormous gravity from Jupiter. Everything, you know, pretty much same throughout the solar system, in different amounts. So the effects of tidal heating due to the gravitationally derived flexure of rocky materials is what makes Io a hell on Earth. It's the most volcanic system, the most volcanic body in the solar system. It's constantly erupting material from within. Right there, that's a volcano. That's a volcanic plume. It's really big. Ice also has insulating properties. So if you heat something up, you cover it with ice, it tends to stay warm. This is the principle behind the igloo. How do they stay comfortable in an igloo? Well, it's cold outside, but the ice acts to insulate. Okay, we've had two that I know of, missions out there. Oh, you can tell that a lot of my information comes from NASA, by the way. Galileo, Voyager, and we got a lot of data from them. We got a huge amount of data from Galileo. We got quality data from Galileo. And other than that, you know, we can look at it through telescopes. We don't have much else. This was Galileo. Some of the stuff that Galileo brought back for us or sent to us. Yeah, there's another proposal somebody at the Jet Propulsion Lab came up with that never saw the light of day, called Project IcePick, the Europa Ocean Explorer. This is JPL, Jet Propulsion Laboratory. The guy had some free time. I think it's a great idea. It's almost outlandish, but it would just be great if we could do this, okay? You send a probe to Europa. It's robotic. It deploys a robot that has a drill that drills into the crust and then turns into a submarine, a robotic submarine that, you know, looks for stuff and finds life, like right there. Great idea. It never saw the light of day. Okay? So, you know, like all really, really cool ideas, a lot of them didn't see anything. Project was mostly speculative. They're talking about the EJSM Laplace, Europa Jupiter System mission. Laplace was a big joint effort between the European Union, Japan, America. Well, from what I understand, America's pulled out of it. You know, we're not going to do it. So, budget cuts. Yeah, it would be neat. I mean, I think it's cool. Cool.
You think this is worth doing?
I think it's worth doing. I mean, I do agree that we have some stuff to take care of on this planet right now. I agree with that, but we have to keep discovering new things. I mean, this could be a resource for us. An entire planet with a planetary ocean. I mean, okay, since there's probably water or slush, could there be life? Well, you have things on Earth called extremophiles. You have archaea, and you have these things called methane worms that live in methane clathrates, like deep in the ocean or something. Scary looking thing. It likes really cold weather, like sub-zero weather. These psychrophiles, especially the archaea, some of them like weather that's like negative 50 degrees or something like that, negative 50 degrees Fahrenheit. They can thrive. You have extremophiles that can thrive on high levels of radiation, extremophiles that thrive on high temperatures. Life is very adaptable and can do some strange things. So there's no reason why it couldn't be on Europa. You know? Okay, there's my citations. The third one down, Richard Greenberg, he recently wrote a book called Unmasking Europa. I think that's the name of it. I personally want to read it. He's done an enormous amount of research on Europa. And he's been doing it for years, too. And you have all these other folks. A lot of your campuses that do planetary science or planetary geology, Brown University, University of Arizona, and the University of Tennessee. So their campuses. And Georgia Tech. I looked up Georgia Tech, and they have people doing planetary geology and planetary science on that campus, too. I think it's important to know what's out there. It's important to clean up our act here, but at the same time, we should be thinking about this, in my opinion. Okay. Thank you.
Thank you.
Any questions? Any questions? Yes?
These different features like the cycloidal, crack features, or any things like that in Earth, places where there's ice, floating ice?
Not ice so much, but you got to think of it as this ice is a completely different kind of ice. There's 15 different kinds of ices, and they all have different properties. And the ice that's on Europa, because of extremely low pressures, extremely low temperatures, is almost completely different from our ice. And that's why they were investigating perlite, because these researchers, these guys, Oyarzun, Viedma, Di Ignacio, have kind of looked at perlite. They're geologists, and they know, okay, well, I know what this rhyolite glass is, okay? And they did a bunch of tests, and they put it through some models, and they figured, it looks like Europa's ice is similar in structure to this rhyolitic glass. Now, rhyolite is, of course, a type of volcano glass, you know. So, rhyolite's a rock.
So what would be the view, like, if you were standing and you're looking at Europa?
That was one of my questions. You gotta answer that. Well, what did I say? What did I say? Okay, like, the tallest feature might be 100 meters. That's not too big. That's like a tall hill. Those ridges, some of those lineaments are fracturing like this. You get sort of tectonic activity there, because you have some subduction, you know, of something, probably a thinner ice over a thicker ice, subduction, and you end up with these ridges. So if you weren't standing next to a ridge, which would probably stretch from horizon to horizon, it would probably be flat. It would probably be just like standing on a flat, icy plain. And there's domes too, but the domes can be, you know, maybe a meter high. It's really pretty featureless. I mean, it's ice, a bunch of ice in places cracking. Yeah.
So does Europa have like an atmosphere, all the different layers and stuff? So I know you said it's oxygen was trapped in there.
It's got a little bit of oxygen, and that's thought to be outgassing that's coming from within Europa somehow. Because it's not holding oxygen to its surface like on Earth. There's hardly any gravity there. So where's it coming from? Because some of it could be coming from that storm that storm of ions that's coming from Jupiter, but probably something that's outgassing from those cracks that are on Europa. So those cracks, you're also getting some sulfates, you're getting salts in the water, dissolved in the water too. There's some sort of outgas as well.
I was curious, you said that this was a project that you worked on a little bit while you were in grad school, or just something that you learned about while you were?
Oh, I did it, yeah. I actually did it between the time I was an undergraduate. I did it as a project.
Okay, so kind of,
Then I became a grad
what part of this was your kind of expertise? Where did you get involved in?
Oh, my expertise is water. I'm a hydrogeologist. So I got involved with it because there's a lot of water up there. And thinking about all the pressure conditions, you know, what's the hydrostatic pressure, you know, at the various levels, you know, down in that ocean, if there's an ocean. And I believe there's an ocean. I think there's enough evidence. You know. So it's water. Water is really good. I almost did Io, because Io's cool. I mean, it's volcanic, you know, really neat. Europa has possibilities. If there's really water down there, someday we could use it as a resource, you know, hopefully wisely.
Why do we not see water on any other road other than Europa?
I'm not sure. Something happened, something's occurring there with Europa that allows it to be that way. Now, one of the other Galilean moons has water on its surface, and Mars has water on its surface, if I'm correct.
In the past.
In the past. Now,
Water.
yeah, right. There's water features, like stream cut features that look like some sort of stream cutting through an eroding, you know.
Oh, there has been some new evidence. If you look at the size of craters, so you've got a big hole in the ground, and there are places on craters where it appears as though material, and when I say recently, you guys know from our geology class, most of the time when we're talking about recent, we're saying, oh, you know, millions of years, that's pretty recent kind of thing. This is within decades. Okay, so from the first time we took a picture to the last time we took a picture, it seems like there's been some stuff that trickled down the side. As if there were undersurface reservoirs where below the surface there was enough pressure that the H2O could exist as liquid water and then trickled out the side of this chasm, basically. So there's a lot of H2O in a lot of places.
Mm-hmm.
It's just it's special to have water.
Yeah, and So you'd have to have a hydrological gradient, you'd have to have a high head and a low head, because you got a steep. So you got high head, low head, you got area, something's flowing over an area, you got material, that's Darcy's law. That's what's happening. You guys in my class are going to learn about Darcy.
Well, there's also Enceladus, Saturn's moon. There's also believed to be, or hypothesized to be, maybe a pocket of, liquid water or something near the South Pole.
Yeah.
I had a talk once actually from someone who came from JPL at the Atlantic Times Tavern. She talked about that, and it was pretty amazing. So, there might be several places where the conditions are right for pockets of liquid water.
I have two questions. First of all, are they hypothesizing water on Titan, or is that just nothing but metal?
Not on Titan. I think Titan's overall too cold.
Some of the ice would be H2O, but no liquid water.
Yeah, it would be way too cold. Yeah, notice just Enceladus, as far as I know. Because Enceladus also has these cracks.
Yeah.
Where you get they call them geysers. That spray out into space.
Yeah. Yeah, some of these bodies have they undergo cryovolcanism.
The water has a lot of ammonia mixed in, doesn't it? That makes it able to not freeze.
Yeah, maybe. I'd have to read up on it again. But that is pretty amazing.
I think it's, Jupiter and Callisto. I think it's Callisto that has some, again, magnetic field.
Yeah.
Signatures that there's some water.
Callisto has a magnetic moment. It has a magnetic field. Europa has a magnetic field because it's an induced magnetic field from Jupiter. It doesn't really have its own magnetic field.
Ganymede's the one that has its own.
Okay, Ganymede.
And Callisto, I think, has this other induced field, which makes them think that there's got to be that electrical conductor, which would be the brain.
Yeah, Io has a induced magnetic field. You took Jupiter away, and Io wouldn't have one. Io is an extreme example of tidal flexing, of tidally induced heat, because it's constantly erupting. Materials are constantly melting, erupting, and being, assimilated. I don't think there's no tectonic activity. So nothing's productive. That's another reason, what's going on there. Most of our volcanism is due to tectonic activity. There's none on Io, so it's pretty neat. I think we ought to go to this place. My second question: what's the Atlanta Science Tavern?
I know, I wrote that down.
Oh, okay.
What's that?
Well, I think it is something informal through the Georgia Tech community, maybe.
Oh, okay.
I can forward you the thing.
I was just wondering. That sounded kind of.
Yes, they have interesting talks about all kinds of issues. Some are astronomy, but I think there's also like a math person, that speaks, or
neurobiology.
Yeah.
Yeah, I can forward you the
Hopefully that
announcement.
statistician. I'd like to brush up on my statistics. That's what I'm looking for.
But yeah, they have they bring in like the real people.
Yeah.
They have connections.
Not the interested amateurs. That's really cool. Really cool. I'm going to get that book, by Richard Greenberg's. He kind of took all his research and he made it into a sort of a layman's read, Unmasking Europa. It came out like 3 years ago. On my Christmas list.
Given the pressure differences, if there is a subsurface ocean there, can you speculate about what the temperatures would be in that?
That's a good question. Well, given the fact that ice acts as an insulator, and given the fact that there would have to be a constant level of heat, probably wouldn't be that warm. It would probably be just right above freezing. But depending on what kind of heat that the crust, the interior, the rocky interior is giving off, you might have something that's not so cold near there. One of the speculations is how much exactly, and people have done just pages of math, how much tidal flexing occurs and to what extent does it produce heat? Enough to keep that liquid, but to keep it very warm? Not sure. And it's pretty much a given that there's nothing like magma or anything like that, although some people have speculated there might be some sort of volcanism derived from the tidal. If there's volcanism down there, so if the tidal flexing is enough to cause some sort of volcanism, magma, melting of rocky materials, which could happen because you've got an influx of water there, where we've got water seeping into tectonic plates, you drive the melting point down. So if there's volcanics down there, if there's some sort of magma, then it might actually be pretty warm.
Well, the pressure differences would also affect the freezing point quite a bit, too.
Yeah, that's true.
How much
The salinity effect of it all, too. They think there's a lot of brine there. What's that?
Is there any information about how briny it is, what the salinity is?
They think it's significant enough to see the spectral signature from Galileo.
So more than the Earth's ocean.
Brine, yeah. Brine is defined as being extremely stable, like you're overloading it with stable.
Like, how does that compare to our ocean?
It's probably a lot more salty. And that would affect, that would affect the breathing.
Yeah.
Right.
Yeah, see, like I said, I'm a professional geologist, so I'm approaching it that way. The whole astronomical aspect of it is kind of what I'd like to learn more about. It's fascinating. I mean, how did this planet, this little moon, get like this? And what's Jupiter all about? I'd like to know more about the composition of Jupiter too. I know there's a metallic layer of hydrogen there, which is kind of interesting.
Juno's on its way there to find out.
Yeah. See, when is it going to get there?
5 years.
Okay, that's good. See, that's something in our lifetime.
I know. I'm grasping for any straw.
That's right.
For a fictional view of galactic survival at low temperature, you go see the remake of The Thing this week.
That's right. Why are they doing that? They had James Arness, and they had that one in the 80s, which was good. John Carpenter's was great. But, I don't know, maybe this one will be good.
So that it boosts that gravity, rather than going straight to fossil fuel. It's a lot more expensive.
Cheaper to take a long way.
Yeah, especially if there are no people on board that need to be kept alive.
Yeah.
Yeah.
All right, that's pretty much it.
You see?
Yeah.
If you're in my class, just, get your sheet. It's due Monday. You don't have to worry about it. Unless you want, you're done. You get your extra credit early.
Yeah.
So I have.